So step 4 is also an investigation on the, it's an investigation of the load drive requirements. And this also is an aspect that cannot be improved by negative feedback. We can deteriorate it with negative feedback, because if we need to drive extra current into the feedback network, then we need to have devices that can drive more current, because the feedback network also needs current. But we cannot improve the requirements with negative feedback. At best, if we have non-energetic feedback elements, the drive requirements for the controller are equal those of the amplifier. That's what you can say. And that's what we have seen in our investigations. So here, that's what we are going to do. The next step, you see, we have orthogonal steps. There might be a little bit interaction here, of course, with the feedback network, as I explained. That is the blue dot again, because the feedback network might increase the energy storage or require a current or voltage and has a passive part, and then it has power dissipation. For this, we need to do a nonlinear simulation, so we need to use LT-SPICE. And we are going to design the same design aspect, but now also including the voltage level of the controller output stage. So that's what we do, and the feedback network is still involved. So if we have a structure that requires more power in the feedback network than another structure, then that can be an advantage. That's what the interaction says. So for the active antenna, we are going to design a CS stage with sufficient static and dynamic drive capability. So, and we have to determine IDS, VDS, WL, and the multiplication factor. That's basically all we have to do. And if we have found a simple CS stage to do so, we know that we can increase the performance to cost ratio by applying balancing with a complementary, parallel, or push-pull output stage. And we can have less quiescent power, but we can still drive high currents to the load. That might be interesting. So if you are investing showstoppers, you better start there, because that is the best situation you can have. So that's what we do. And here you see there was an, I think you remember we did this, the files are available. We made a output stage, we biased it, we designed 2 transistors, and we checked the characteristic, and people did it in various ways. This is only static. You also need to do it dynamic. This 2.5 PF represents the feedback capacitance, which can be considered in parallel with the signal path. So that is basically the test setup, the test bench for the output stage. So how does the design proceed? Because that is interesting, of course. Do we just use this schematic and try something with W or L, or do we have a kind of starting point which is clearly defined? We start with the smallest value for the length. Why? Because if you take a longer value, you need for the current, for the same current drive, a higher voltage drive, because the transconductance is lower of the stage. Which means that you might say, oh, I don't have such a drive voltage available in our power supply, and you say it is a showstopper, but it is not, because you made the transistor too long. So if you want to be sure that you find a showstopper, a real showstopper, and no competitor can do it smarter than you do, then we start with the smallest value of the length. It doesn't mean that later on maybe you want to increase the length of the transistor for some other whatever reason, but at the point of investigation of showstoppers, we start with the smallest length. Then how do we do this for the PMOS and the NMOS? Well, the best way is to start with a ratio that is 1 over the mobility ratio. So let's say if the mobility of an NMOS is about 4.5 times better than of a PMOS, then the PMOS should be with the same length 4.5 times wider than the same NMOS. And then you have, or you take 4.5 times more transistors in parallel than for the NMOS, or you do some combination of that. That will be a nice starting point, and of course you can optimize it later. Optimization is like different thing. Here we are investigating showstoppers. So then we determine W and M such that the load can be driven with a sufficiently small voltage. Now let's see what we have here. Here we have, you can step, you can, let's say, make the width function for both of some parameter and step that parameter and see if you can make 320 millivolt, because that is what we need, 320 millivolt with a decent input swing. Here, so you see if you need an input swing of 500 millivolt and the thing is completely clipping, you can imagine you will have a huge distortion and you need an extremely high loop gain to get to low IMD. So there is some compromise, of course. So I aimed for this green one. So number 1, 2, 3, 4, 5, this one. This green one. It looks like quite linear when we go here through the origin, and for a 320 millivolt output you need about 200 millivolt drive, and then it is fairly non-linear. The game has really changed, but let's say later on we can take higher quiescent current. So this is a function of the quiescent current and not a function of the width, of course. This is after I have selected the width. So for the PMOS, it ended up with 40 micron and 10, and for the NMOS, 40 micron and 3. So this is a factor of 3.3 instead of 4.5, but it looks quite symmetrical to me, and optimization can always be done later. The bias voltage here was pointed, so it was 1, 2, 3, 4, 5. That's 4 steps of 50 millivolts. You see, make steps of 50 millivolts, so it was 200 millivolt bias voltage here. So in the total, it was 400 millivolt between. This resulted in a quiescent current of 1 milliamp and drive requirement of plus and minus 200 millivolt to have 320 millivolt at the output. So that is a starting point.